Okay, in this lesson we're gonna look at a method of proof, which is a well-known method of proof and a very popular one, mathematical induction. Now, if you have a look at what the title of this chapter 1 actually is, because we've sort of said we're doing sequences and series, but it's actually more broadly mathematics as the science of patterns. The science of patterns. The science of patterns. So what we are doing is looking at patterns. So we've had a look at different types of sequences, arithmetic, geometric, and examined those. But we're looking at the science of patterns. So what we're going to, as part of this area and part of this section of work, we're going to look at a method of proof, mathematical induction, that uses a sort of a pattern technique, a technique or a method whereby we establish a pattern of Okay, in this YouTube lesson we're going to have a look at a method of proof, a method of proving a formula, a conjecture, or a hypothesis, but the method's called mathematical induction. I'll explain what that means in a moment, particularly the induction bit. But just more generally, chapter 1, which we're in, is actually titled The Science of Patterns, or the mathematics behind the science of patterns, or something like that. Mathematics as a science of patterns. So we're looking at patterns generally, and mathematical induction is a pattern-based proof method, if you like. It uses patterns in order to come up with its proof. Now, we'll go on to look at that and explain that. But the induction bit of it, what does induction mean? What's the mathematical induction? So if we think about induction and actually deduction, induction means going from taking some specific examples, so from specific to, so we look at some specific examples, we look at some specific cases, and we use those in order to formulate a general proof. So from going from specific to general. Deduction goes the other way, just for out of interest. Deduction, we go from a general theory, from a general statement or theory, to specific cases. So that's where we've got a theory, something, and then we go to specific cases, and in order to establish the validity of what we've got. So what we're doing with induction is we're going to start, and you'll notice that we start with specific examples, and we build a case based on that in a way that forms a pattern and a nice little proof. Okay, so what we're going to do firstly, we're going to do a few examples just to see how this works. The first one, actually, what we're going to do initially is go through the 3 steps. Okay, so I'll just pause the video while I set up a few notes. Okay, so I've written out the 3 steps here that you need to go through to make this proof, to complete this proof by mathematical induction. So whenever you're asked to use this method, these are the 3 steps. So the first step is usually the easiest. Prove that the statement is true for a starting value, usually n equals 1. This will be really much clearer when we do an example in a moment. But this is going back to we're being specific. So we prove true for a specific value. Really important. We've got that. We get that initial value sorted out. The second step and the third step sort of go together, because now we're going to assume that the statement is true for n equals k. So for any value of k, we're going to assume that it's true. And then linking in with step 3, which is using that assumption to prove that if it's true for n equals k, then it's also true for n equals k plus 1. Now, as a group of 3 steps, we show it's true for n equals 1, and within 2 and 3, we show that it's got this sort of domino effect now, that if it's true for one value, then it's true for the next value. So if it's true for n equals 1, these 2 steps, 2 and 3, show that if it's true for n equals 1, then it must be true for n equals 2. And if it's true for n equals 2, it must be true for n equals 3. And this domino effect that then will prove that it's true for all integer values of n. And that's what we're looking at. We're looking at integer values. So we're going to do an example. And it's, I'll write the example up. So I'll pause for a moment, write the example up, and we'll go through it. Okay, I've written up the example here. What we're going to do is essentially use mathematical induction. this three-step proof to show that, or to prove the sum formula for an arithmetic series. So, okay, so let's go through it. Step 1, and we're just going to be quite clear about our steps here. So we're going to go 1, and what our task with 1 is to prove true for n equals 1. Now, in this case, it's implied, isn't it, that n is the term number, represents the term number, so it starts at 1 and goes up from there. So we'll start with the lowest value, which is n equals 1, and we'll prove it true, the statement true for n equals 1. So, so we go S1 is equal to 1 over 2. Sorry, that's not the best starting point. So when we're proving true for n equals 1, the best thing, and in step 3, is to just say left hand side equals right hand side equals. So the left hand side equals S1, which we know the sum of one term of an arithmetic is just the first term. So that's U1. Now the right hand side, we're going to show that's also U1. The right hand side when n equals 1 is 1 over 2 U1, plus when n equals 1, that's 0d. So that's 0, so it's a half by 2u1, which equals u1. So we've got, therefore, left-hand side equals right-hand side. And so we've proved it's true for n equals 1. It's usually a very, very trivial part of the process. And in fact, 2 is very quick as well, because in 2, all we're doing is we're going to assume that it's true for n equals k. So assume true for n equals k. So all we do here is say, right, we just sub k in for n, and we write, so therefore we're assuming that sk is equal to k over 2, so this is for some value of n, we're just letting that be k. K over 2 to u1 plus k minus 1 by d. Okay, so we're going to assume true for n equals k, so steps 1 and 2 very quick. Step 3 is where all the work is. In step 3, we need to prove true for n equals k plus 1. Now, we're going to use, as it says here very important, we're going to use the assumption to prove that if it's true for n equals k, it's going to be true for the next one. Okay, so we're going to use this assumption, and we'll talk about how this is a compelling proof once we've got through it. So, first thing we need to do is we need to state, so what this means is, therefore, we need to prove that sk plus 1 is equal to k plus 1 over 2 u1 plus, this is k plus 1 minus 1, so it's just kd. We'll close the brackets there. So that's what we need to prove. So as with step 1, we're going to have a left-hand side, right-hand side approach. So we're going to go, right, left-hand side equals, it's equal to sk plus 1. Right, now what's that equal to? Well, that's going to be equal to sk. So this is where we use this. We always go back up here and use what we can. So that's equal to sk. So it's going to be the sum of the first k terms, then plus the k plus first term. Now the k plus first term is, if we think about the nth term of an arithmetic, it's the first term plus n minus 1d. So if we look at the k plus first term, it's going to be u1 plus kd. So u1 plus kd. So that's going to be our left-hand side. Taking the sum of k plus 1 terms, we're going to use this. So it's the sum of the first k terms, then the next one, the k plus first term. So, right, so now we're going to substitute this in for sk. So it's equal to k over 2 u1 plus k minus 1d plus u1 plus kd. Okay, so what we're going to aim to do now is to rewrite this so it looks exactly like the right-hand side. So the best thing to do here is probably to run through, maybe expand this first, so we get k over 2 u1 plus, so it's just a bit of algebra now, kd minus d plus u1 plus kd. Alright, let's expand this out. So k over 2, 2u1, that's u1k, u1k plus, what's that, k squared d over 2 minus kd over 2 plus u1 plus kd. Okay, we need to get this tidied up a little bit, don't we? So I can see where the over 2 is going to come from. K squared, now we've got any like terms, we've got a kd here and a minus a half kd, so that gives us a half kd, so that really the tidy up is u1k plus u1 plus k kd on 2 plus kd on 2. Now if I take out, if we take out kd, take out a half, then we would have okay, so I'm sure there's lots of ways of doing this. I'm actually going to back down from that method and just factorize this in pairs, because I can see u1's a common factor here, so I can just put a k plus 1 in there, and I can see kd over 2 is a common factor here. I've got a k plus 1 there. That's a common factor of k plus 1, so now I've got k plus 1 by u1 plus kd over 2, and now what I can do is I can say, okay, let's get that over 2. That's going to make that 2u1, and this is going to make that kd, and that is what I have there on the right hand side. So I can say that's equal to the right hand side, and so therefore if statement true for n equals k, then also true for n equals k plus 1. So we proved that. We proved that because we've used that statement, the assumption that n equals k, to prove n equals k plus 1. But what we did at the outset in the first step was to prove it's true for n equals 1. So we know it's true for n equals 1. Therefore, if true for n equals 1, then also true by this first statement. If it's true for n equals k and k equals 1, it's also true for n equals k plus 1. So if true for n equals 1, which it is, then also true for n equals 2, and if is true for n equals 2, then also true for n equals 3, etc. So our final statement is therefore true for all integers n greater than or equal to 1, which is the proof. Use mathematical induction to show that some of the first n terms is that. So we've used the method of mathematical induction to prove that that is true. Now it's kind of wordy, it's kind of clunky, but it's really powerful. It does a lot of does do a lot of mathematical proofs for us. Is a really effective technique. And just to recap, the induction means we're going from specific to general, and you can see that's exactly what we've done. We've taken a specific value, and then we've generalized from there. And as a three-step process, we're able to use that domino type effect to demonstrate that that statement is true for all values of n. If it's true for n equals 1, it's going to be true for n equals 2, and so on and so forth. Okay, we'll leave it there. It's a 14-minute lesson. I was going to do some more examples, but it's each example does take quite some time. So we'll look at some other examples in class, and then we'll be ready to do exercise 1H and 1I. So they're the next two exercises that we'll do that are on this work on mathematical induction. Okay, I'll see you soon.